I'd like to talk to you about what I consider to be the most beautiful statement on the importance of inverse operations. It's not this one, it's this one. But first, I'd like to talk to you about what math is. I've taught many levels of math for many years, and I think the answer depends on who you are and what you want to do with math. Math is about a lot of different things, but for most of us, whether we know it or not, math is about learning how to do something, like adding to, and then learning how to undo it, like subtracting to. If that sounds kind of silly, if it sounds like going around in circles, you may be right, but there's a lot of value in learning how to do and undo something, and there are many things in life that work like this. On the very simple end, we open and we close doors. A slightly more complicated task would be taking things apart and putting them back together. To be successful at just about anything, our brains need to be able to take the big picture and break it down into small, understandable parts. And then, we need to be able to take the small parts and put them together so we can understand the big picture. If we understand the process going forward and backward, then we really fully understand the process and we can take full advantage of it, regardless of which direction we need to go. For example, a manager who really understands what happens at each step on the factory floor will be a better manager, and a factory floor worker who understands the end goal of production will do a better job with their small role. This process of doing things and undoing them happens all the time in math. We start by learning how to do something fairly easy, like adding. Once we know how to add, we learn how to undo adding by subtracting. As we learn these two skills, most people find adding easier than subtracting, and this is generally true with math. Performing an operation is usually easier than undoing that operation. Multiplication and division have this same type of inverse relationship. They undo each other. Multiplication is pretty easy, while division can be a lot harder. And we can multiply by 0, which is pretty easy, but we can't divide by 0. Along with multiplying and dividing, we learn how to square, then we learn how to find square roots, then we learn how to cube, then we learn how to find cube roots. We might even show how these operations undo one another like this. As we learn more math, we find there are little things we need to be aware of when undoing mathematical operations. For example, we might get decimals or fractions when we're dividing, but the first real trouble comes when we learn to solve equations by taking square roots and cube roots. Why do we have to put a plus or minus sign when we take the square root, but not when we take a cube root? Moving forward, exponents are pretty easy to understand, but their inverses, logarithms, are much more difficult, and we can't take the log of a negative number. By the way, figuring out why we can't take the log of a negative number and why we can't divide by 0 are interesting investigations in the complexities of inverse operations. Then we get to trig functions and inverse trig functions. Trig functions take angles and give the ratio of the sides, while inverse trig functions take the ratios and give angles, but there are some restrictions. We even learn how to do and undo math when graphing. We learn lots of ways to take a linear equation and graph a picture of all the solutions. But learning how to take a graph of a line and find the linear equation that produced that line is much more complex. The ultimate statement on the importance of inverse operations, that's accessible to most people who study math extensively, comes when they encounter the Fundamental Theorem of Calculus. This is the formula we started with at the beginning of this video, but before we get to it, let's take a look at the full theorem. There are two parts of the Fundamental Theorem of Calculus, which we're going to refer to as the FTC. What some people call Part 1 looks like this. It helps us evaluate definite integrals and find the signed area between the curve and the horizontal axis using antiderivatives, which, as the name suggests, undoes differentiation. Part 2 of the FTC is a strange statement that looks like this. We'll take a closer look at this in a minute. Even though finding antiderivatives can be hard, the evaluation part of the FTC is pretty easy, and most people have some fuzzy memories of it, even years after learning to integrate, just like they have fuzzy memories about how to differentiate power functions. Part 2 of the FTC is much more difficult to understand and use, but it's probably the most important. What does it really mean, and how can we make it more understandable in terms of inverse operations? I tend to remember phrases more than pictures and formulas, so if I can find a phrase that describes an idea, then I can remember it. For example, the inverse of a matrix is 1 over the determinant times the transpose of the matrix of cofactors. Try it out, it'll work. And when teaching the Pythagorean theorem, I don't have students memorize a squared plus b squared equals c squared. Instead, we say leg squared plus leg squared equals hypotenuse squared. It's the same idea, but has more information about how and when the theorem works. So for the Fundamental Theorem of Calculus, I teach this phrase. The derivative of an integral is the integrand with the upper limit plugged in times the derivative of the upper limit minus the integrand with the lower limit plugged in times the derivative of the lower limit. Thinking about the FTC using this phrase incorporates many of the ways these operations undo one another. It incorporates rules of differentiation, it incorporates concepts involved in changing the direction of integration, and we can even see elements of how we evaluate definite integrals. Let's take a closer look. Differentiation and integration are the two main branches of calculus, and they are inverse operations. There are many good explanations and visualizations on YouTube as to why the derivative of the integral shown here is the integrand with the upper limit plugged in. Essentially, this says if you integrate f, then differentiate the result, you get back to the original function f. These operations cancel each other out. They undo each other. But how can we start with something so compact as this and end up with something so much more complex just by changing the limits of integration? Just as with other inverse operations, differentiating to undo this integral introduces a bunch of unexpected stuff. Why are there two f's? Why not just one like we had before? And where did the dv dx and the du dx and the minus come from? Let's start by evaluating the definite integral from a to b. Now let's apply the inverse of integration by differentiating each side with respect to x. This gives us a trivial result because we're finding the derivative of a constant, which is 0. Now let's change the upper limit to x and see what happens. When we differentiate, we need to use the chain rule and do a little bit of simplification. This is the result we were looking for, and it's in nearly every lesson you'll see on the FTC. Notice that the derivative of an integral is just the integrand function with the upper limit plugged in. Changing the direction of integration should change the sign of the result. You'll notice the f of x comes second, so it has a negative in front of it, so we get exactly what we'd expect. But what happens if the upper limit is itself a function of x? Again, we employ the chain rule and get the following. It's an interesting result because the dv dx remains even after simplifying. Remember, it's there because of the chain rule. So, what happens if both the upper and lower limits are functions of x? Surprisingly, this goes pretty quickly because there's not much simplification. This is the result from the beginning of the video. The derivative of an integral is the integrand with the upper limit plugged in times the derivative of the upper limit minus the integrand with the lower limit plugged in times the derivative of the lower limit. Here's an example with some simple functions. If you know some basic differentiation rules, you can try one yourself. One of the amazing things about this process is that we didn't once have to find an antiderivative. Think about how useful that might be if the integrand was a function whose antiderivative was not known. I sometimes show my students math problems where what we plug in doesn't matter. Math uses a lot of arbitrary symbols, and differentiation and integration will still undo each other. I remember looking at the Fundamental Theorem of Calculus for the first time and being so confused. I could find antiderivatives and I could evaluate definite integrals, but the magnitude, beauty, and simplicity of the theorem escaped me until I started teaching calculus. I spent a great deal of time thinking about how these two branches of calculus follow the same pattern of so much of what we do in math. We learn how to do something, then we learn how to undo it. Developing and growing brains that can understand processes like these is really what math is all about. We want people who can both construct the big picture from the small parts and identify the small parts in the big picture. I hope this helps demystify some of the details of the Fundamental Theorem of Calculus. Thanks for watching.